Welcome to Yurix AI. This is Lecture 7 of LLMs from Scratch, Zero to Builder. I'm absolutely thrilled to have you here today. You know, over our past few sessions, we've been unraveling the mystery of how large language models actually work under the hood. But today we're taking a massive leap forward. We're not just talking theory anymore, folks. We're rolling up our sleeves and literally building a crucial piece of the architecture right from the ground up.
Here is our roadmap for today. We've got 6 key steps to cover. First, the 2 steps of tokenization. Second, importing the dataset. Third, splitting text into tokens. Fourth, converting tokens to IDs. Fifth, building our Python tokenizer. And finally, number 6, special tokens. Okay, let's dive into this.
Listen, if there's one single thing I want you to take away from this entire explainer, it's this quote right here. An LLM never sees letters. Text is first split into tokens and turned into numbers. Seriously, this is our North Star for today. Everything we're going to build revolves around this one exact philosophy. Think about it. We humans, we read in words and letters, but computers, they only read in numbers. So before our AI can generate a beautiful poem or, write complex lines of code, we have to build the bridge that translates our human language into machine math.
All right, Section 1, the 2 steps of tokenization.
So I want to give you a very simple mental map to hold on to as we get into the code. Tokenization really just boils down to 2 super straightforward steps. Step 1 is creating tokens, and Step 2 is creating token IDs. If you just keep this basic 2-step progression in the back of your mind, you'll never get lost in the weeds. Let's break down exactly what each of these steps actually means, starting with the first one.
Let's define this right off the bat so we don't get bogged down with confusing jargon. A token is simply an individual word or a special punctuation character that we've extracted from raw text. Imagine you take a sentence and literally chop it up with scissors. Every single word you cut out, that's a token. Every comma is a token. Every period is a token. It is the absolute smallest distinct unit of our text.
Once we've got our tokens, we move right along to Step 2, which brings us to our next definition. A token ID is a specific integer number assigned to represent a unique token for the computer. Going back to our North Star idea, remember, the machine only understands numbers. So, if our token is the word apple, our token ID might be the number 5. This specific ID is exactly how the LLM will identify and process that word.
Moving on to Section 2, importing and loading the text dataset.
Now, in the real world, big companies train these large language models on gigabytes or even terabytes of data. We're talking millions of articles and hundreds of thousands of books. But hey, we don't need a supercomputer today. For our explainer, we're going to use a highly manageable text data set of exactly 20,479 characters. Specifically, we're using a classic short story by Edith Wharton called The Verdict. It's honestly the perfect size. Small enough to run instantly on your everyday laptop, but complex enough to teach us all the core mechanics of text processing we need.
Which brings us to Section 3, splitting the text into tokens.
So, how do we actually chop up this text? To achieve this in Python, we use something called a regular expression, which developers usually just call regex. A regular expression is simply a sequence of characters used in code as a search pattern to find or split specific text. Think of it kind of like a highly advanced Control+F or find function. You definitely don't need to memorize the complex syntax right now, but just know that we're using Python's built-in re-library to tell the computer exactly where to make its cuts. Specifically, we're targeting white spaces and punctuation marks.
And this brilliantly illustrates exactly what that regex code does. Look at the raw string hello world. Our regex tool sweeps through that text and splits it up perfectly. It separates the word hello from the comma, it separates the word world from the period, and it even filters out the empty white spaces to save us memory and computing power. Pretty cool, right? What we are left with is a super clean, organized list of strings. Hello, comma, world, period. Just like that, Step 1 is officially complete.
All right, Section 4, converting tokens into token IDs.
To map our words to numbers, we've got to build a vocabulary. A vocabulary, in this context, is a unique, alphabetically sorted master list of every single token found in our text dataset. Imagine it as the essential master dictionary for our LLM. It's literally how the model knows what words exist in its universe. If a word isn't in this vocabulary, well, as far as the model is concerned, it basically doesn't exist.
When we process our text dataset, Edith Wharton's short story, and filter it down to only the unique words and punctuation marks, we end up with a vocabulary size of exactly 1,130 unique tokens.
We take these 1,130 tokens, sort them alphabetically, and simply number them from 0 to 1,129. That assigned number, that is our token ID.
Now for the really fun part, Section 5, building a simple tokenizer class in Python.
I always like to think of this tokenizer class as an everyday childhood toy, this secret decoder ring. Our class has two main jobs. First up, it has an encode method. This method takes human text and translates it into secret numbers, our token IDs. Second, it has a decode method. Later on, when our LLM actually generates a response in numbers, the decode method translates those numbers backward through the ring, turning them back into human text we can actually read and understand.
Here, you can see the core logic inside our Python class. When we initialize the class, we feed it our vocabulary. It then stores two dictionaries. The first one maps strings to integers for encoding. The second one is simply the exact reverse. It maps integers to strings for decoding. By storing the vocabulary in both directions, our secret decoder ring allows us to translate back and forth seamlessly. Boom! We now have a functioning tokenizer. But wait, what happens if we input a new word like hello that wasn't in our original training vocabulary? Well, it would crash. To fix this, we're going to need a few upgrades.
Which leads us to Section 6, Special and Additional Context Tokens.
To handle these real-world complexities, we upgrade to a simple tokenizer v2 by introducing some special tokens. For example, the unknown token. If our tokenizer encounters a word it just doesn't recognize, instead of crashing, it simply replaces it with the unknown token ID. We also have end of text, beginning of sequence, and end of sequence tokens, which act as boundaries. Say you train an LLM on thousands of different books. These tokens tell the model where one book ends and an entirely unrelated book begins. Finally, we have the pad token. When you're processing data in batches, some texts are inevitably shorter than others. The pad token just pads out those shorter texts so everything is a nice, uniform length for the computer to process efficiently.
For our simple tokenizer v2 today, we're just going to add the unknown token and the end of text token. By adding these two special tokens to our existing list, our new vocabulary size expands slightly from 1,130 to exactly 1,132. Now our tokenizer is robust. It's not going to crash when it sees a new word, and it can understand document boundaries like a pro.
So today, we successfully achieved something pretty amazing. We learned exactly how to turn raw human text into numbers by splitting it into tokens and mapping it to a vocabulary. But I want to leave you with a provocative thought as we wrap up. We used just over 1,000 tokens for one single English short story. If a modern LLM needs to learn multiple distinct languages, including complex coding languages, how massive does its vocabulary decoder ring need to become? Think about the sheer engineering required to handle that kind of scale. Like, share or subscribe to Yurix AI for a new lecture every day, hit the bell.